Hello, everyone. My name is Cole Hammett, and I'm working with Teague McCracken and Mike Harry on our final project titled Deep Learning for Southern Leaf Blight Disease Severity Grading via Drone Imagery of Corn. So currently, there's very slow and subjective visual scores that are used to assess foliar disease severity. These are used by corn breeders to identify new genetic desistance, and this is used by corn producers to identify disease severity in massive field settings. And this project reframes disease assessment as a supervised regression task. We're training a deep learning model to predict southern leaf blight severity directly from drone-collected RGB images. And the challenge really lies in designing a system that generalizes across seasons and field conditions while managing large, noisy, and imbalanced real-world data. We're working with very heterogeneous images that contain different lighting conditions, different amounts of weeds, different numbers of plants. And the next slide is a histogram that shows the imbalance in real-world disease severity. We would be able to get a lot of information from those lying in the extremes, but this histogram shows that we've got a score distribution that reflects the natural biology of disease severity.
We attempted to use classification tasks and use frequency-based weights for our loss function to account for this imbalance. However, we saw that regression tasks both trained faster and performed better.
For our baseline model, we started with a simple 2D convolutional neural network with regression. We continued our investigation with going to a higher, more complex uh, custom CNN, and then transitioned into transfer learning with pre-trained models. Uh, this is showing the simple nature of our original simple CNN. From here, we added more convolutional layers, additional pooling, and fully connected layers, but still weren't seeing significant improvement in that model. As we shifted to the off-the-shelf models, we worked with EfficientNet Small and EfficientNet Large and started seeing much better performance, both in mean absolute error as well as an increase in accuracy. We also were able to include regularization through the use of transformers in our data loader, doing image augmentation, which included normalizing, random cropping and flipping, random shadows, coarse dropout, and the addition of noise through Gaussian blur.
We also investigated using vision transformer models. So with this architecture, we have our image, we split it into patches. We use position embedding on these patches, as well as have a global class token. So then we removed these last layers and added our own MLP head with a regression task similar to our baseline. Here we have the transformer blocks. To build on this baseline vision transformer, I attempted to add attention loss to our loss function. So I created these ground truth masks of brown pixels that are surrounded by green. So I basically took the idea that our signs of disease are these brown leaves. So my idea was to take brown pixels and surrounding green pixels, and then we expand the green pixels and take the overlap. So here we have our overlap or our ground truth mask. It's obviously not perfect. It does capture some dirt. However, I use this to train the attention loss after downsampling this, such that we can train our model to pay attention to diseased areas of the plant. Um, and what's nice about this is that we can use this during training. However, during deployment and testing, we only use the original image, so that additional segmentation or mask creation is not needed upon deployment. To optimize this model, I tried adjusting lambda, so either adding aggressive or more subdued attention loss. And I saw best performance with subdued attention loss. And I also optimized the unfreezing or freezing different layers of this model, and I found that unfreezing only the last few layers was the best performance. I also tried dropout in our MLP regression head as well as a learning rate scheduler, both of which improved our performance. So overall, our model performance can be summarized where we saw a significant increase from our baseline, where efficient net small performed the best, but between all three of these, we see similar performance. Um, And we see that the mean absolute error is what we care about the most. So in our disease severity grading, like we said, it's on a 0.5 increment. So that means that these are only off by about one score, which is really good because we're using a very high resolution scoring, whereas most other applications only do severe, mild, or healthy. R squared is great for comparing between models. So this is between our predicted values and our actual values. And accuracy we see is low, and that's why we can see that like this isn't always the best metric because this is really what we care about. And even though our accuracy is low, we still see that it is consistent with our actual scores, and the um, mean absolute error is good. And it's important to mention, oh yes, here's our distribution of prediction errors. So, like I said, efficient at small was the best, and it's important to mention that our evaluation metrics of R squared and mean absolute error were comparable between manual scores. So that shows that our model is good for deployment.